expressing solution concentration. Okay, this part of the chapter has a lot more general applicability and is more important. So we can talk about a qualitative description, which is not involving numbers. And so we can talk about a dilute solution or a concentrated solution. And that means the same thing in chemistry as it does in regular life. A concentrated solution has more stuff dissolved than a dilute solution. So if you think about maybe making orange juice from the frozen concentrate, right? You take that frozen stuff and you squish it out into a big pitcher, and then you add water, right? Like 3 cans of water, and you mix it up. So it started out as a concentrate. It was very concentrated. You can't drink that, right? It's just way too strong. And then you dilute it by adding more solvent, water, and now you have a diluted solution. You could take that and add more water to it and water it down, we sometimes say, and then it wouldn't taste very good either. Then we have a lot of different quantitative measures of solution concentration. Some of these we've already looked at. Molarity. Molarity is the amount of solute in moles divided by the volume of solution in liters. We've talked about percent by mass percent. This is where you're looking at the mass of the solute divided by the mass of the solution. And for percent, we're going to multiply that by 100. So we're going to talk about these different units. So molarity, you can also go back to section 5.2, amount of solute in moles per volume of solution in liter. The molarity of a substance will change a little bit with temperature because the density of water changes with temperature. As you heat the water, it's going to get a little bit larger, changing the volume of the solution, so that changes the molarity. Most of the time we don't have to worry about that. But here we're adding a mole of sodium chloride and water to make a liter of solution, and so we say this is a 1 molar sodium chloride solution. There's 1 mole of sodium chloride in a liter of solution. Molality is not a typo. So if you see that word on an exam, that's not a typo. I do have typos sometimes, but this is not a typo. Molality and molarity. The difference here is we still have the amount of solute in moles, but now instead of measuring the volume of solution in liters, we're measuring the mass of the solvent in kilograms. So if you think about water, right? Water is 1 gram per milliliter, roughly. So a kilogram of water would be 1,000 milliliters of water, which would be a liter. So this is, the number is going to be similar to the molarity, but it's going to be a little bit different. The reason that molality is useful at all is because it's independent of the temperature. So when you're looking at stuff and the temperature is changing a lot, the molarity is not useful because the molarity is also changing. The molality does not change. This is abbreviated with a lowercase m. That's usually italicized. And so, let's add that to the list of m's, right? So we've got capital M, and so that's moles per liter. And then we have lowercase m, and that's meters. And then this script or italicized lowercase m, that's molality, which is moles per kilogram. It wasn't my idea. You can't blame me. Molarity, super important. Molality, not very important. Parts by mass, parts by volume. So this is all based on the general idea of percent, right? A percent is the part over the whole. The part over the whole times 100. Percent literally means per 100, right? So parts by mass, we've got that part over the whole, the mass of the solute divided by the mass of the whole solution, and then we're going to multiply it by a number. For percent, we're multiplying by 100. And so we can take a percent, say 14% by mass, and we can say, well, that means 14 grams of solute per 100 grams of solution. And that's one that we're very familiar with, percentage. We can also do parts per million and parts per billion. Why would we want to do this? Why can't we just do everything in percent? Well, if your concentration is very small, you might use parts per million. You'd have 1 part per million instead of 0.0000, I forget how many, 1 part percent, right? So it's just a way of scaling the units. So parts per million, you multiply by 1 million. Parts per billion, you multiply by 1 billion. And we can also take that concentration, so 15 parts per billion means 15 grams per billion grams. And numbers like this are used a lot in when you're looking at water purity. The local water people will send you, if you're paying the water bill, you get this statement sent to you about once a year. They test the water and they're going to tell you about these levels of different things in the water, right? And a lot of those units will be parts per million and parts per billion. So that's looking at mass. We can also do this with volume. Here, instead of looking at the mass of the solute, we're looking at the volume of the solute divided by the volume of the solution. This is going to be used more for liquids dissolved in liquids. So like 22% ethanol would be 22 milliliters of ethanol per 100 milliliters of solution. This unit, milliliter, you could use liters or microliters. As long as it's the same unit on the top and the bottom, the concentration will be the same. So here's an example of a calculation that we might have to do. What mass of sucrose in grams is contained in 355 milliliters, which is 12 ounces, of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. This is dimensional analysis. So let's highlight what we're given. We got this concentration, we got this density. This thing is in parentheses. It's just kind of like to give you some reference of how big it is. And then it's asking what mass of sucrose is in there. So I'm going to write down these things that I have. So I have 355 milliliters of soda. And I've got 11.5% sucrose by mass. So that means 11.5 grams per 100 grams. So 11.5 grams of sucrose per 100 grams of soda. And then I'm also given a density, 1.04 grams per milliliter. That's the density of the soda. And then what I'm trying to find is grams of soda. No, grams of sucrose. So these are the numbers I was given, and this is what I'm trying to find. One of the hard things for a lot of students is, what number do I start with? Well, let's look at the units. This is just milliliters. This is grams of this per grams of that. This is grams of this per milliliters. These both could be conversion factors, right? They relate to different units. Milliliters is just one unit. You can't use that to convert anything, right? So that plain unit is almost always where you're going to start with, what you're going to start with. So that's what we're going to start with. We're going to start with the soda, and we're going to try to figure out how can we get from milliliters of soda to grams of sucrose. Well, let's look at what we were given. So we've got milliliters of soda here. The density relates milliliters of soda to grams of soda. So that tells me I could convert milliliters of soda into grams of soda. And then I'm trying to get to grams of sucrose. And over here, this relates grams of sucrose and grams of soda. So I could go from grams of soda to grams of sucrose. And then, obviously didn't really need all that space, did I? There. That's the hard part. Now we can just follow the pattern. So I'm going to start with my grams of soda. My volume. We got milliliters of soda. And my path there has 3 arrows. So I'm going to have, what is wrong with me? It has 2 arrows. I need ice cream. That's what I need. 2 arrows, so 2 conversion factors. Milliliters of soda to grams of soda to grams of sucrose. And milliliters of soda is going to be down here, so those cancel out. Grams of soda down here, so those cancel out. So 11.5 grams of sucrose per 100 grams of soda. So that's over here. Again, just keep the number with the same unit it had before. And then grams and milliliters, that's my density. So I've got 355 times 1.04 times 11.5 divided by 100. 42.458 is what the calculator says. And then for sig figs, I should have 3, so 42.5 grams of sucrose in the can of soda. So remember when we weighed out 15 grams of salt for that experiment? And that was a lot of salt, right? It was like a pile. 42 grams of sugar in a can of soda. That's a lot of sugar. When you just look at it, you're like, wow, that's a lot of sugar. Any questions?